So you've seen a decision tree for making a classification of an accident into pilot error or not pilot error. That's a 0 or a 1. Of course, we're going to be using decision trees on Amy's house pricing data. In this particular case, a decision tree might look something like this: the average price before you do any splitting. The average price before you do any splitting is $180,000, and if we did split it on roof style, which is a categorical variable, if the roof styles are flat, gable, gambrel, or mansard, so there are any of those four, then we'll predict a price of $170,000. If it's another roof style, and that's the fifth roof style, and I can't remember what it is, but clearly it's a pretty expensive one, because for that particular roof style, we would actually find that houses in the training data with that roof style have an average price of $226,000, and that is what we would predict on the test data. Let's just go through this terminology. We've seen now two kinds of trees, one where you're predicting classification of a paragraph of text into pilot error or not pilot error, and you can think of a million classifications that you might come across. Some people call these classification trees, as opposed to regression trees, which is what we would say we were building when we use a decision tree on Amy's house pricing data. I just call them decision trees. I think most people do, but that's some terminology for you. Let's think about how we might find the best decision tree out of all decision trees. Imagine we have 500 binary features, and we're going to take a loss function. It could be any loss function: mean square error, Gini, not accuracy. We want to build all possible trees, find MSE of each tree that we have built, and choose the best tree. That is really the only way to make sure we have chosen the best tree, is to build all trees and find the best one. How many trees do we need to build and test? Well, let's have a think. That's going to be tricky. Let's see if we can work it out together. There are 500 ways. There are 500 features that we could use to make the first split. So that is easy. There must be at least 500 trees. But after we've made that first split, there must be 499 different features we could use to split on one side, and 499 different features we could use to split on the other side. And looking at this, it seems to me that it's just going to go over here, 498 each time. I could be getting this wrong, but I just feel like there's a lot of trees. If we went down any one of these all the way to the end, it would be surely 500 factorial. There's loads of different roots down to the bottom, and each of those would be 500 factorial, so it's just an insane number of trees. So in order to find the best tree, we have to do two things. We have to build an insane number of trees, and then we have to measure the train performance, or the loss function, on each of those insane number of trees, and finally we choose the best one. So I've just looked at this slide, and it says it's 2 to the power of something very massive. I'm not quite sure how I figured that out last time I did it, and I wonder if it's the same as the result of those factorials I suggested previously. It doesn't really matter. The point is that it's something insanely massive, and it can't be done. You cannot find the best decision tree. So what can you do? Well, before we say what you can do, one of the most entertaining data scientists on the web is Siraj Raval. I can't recommend enough you having a look at some of his content. I think last year I played this one in the lecture. I find it vaguely amusing. So, if we can't find the best decision tree, what can we do? Well, this is what we can do. Recursive partitioning, we've talked about it already. Given the data we're looking at, find the single best split. We're not going to find all best splits at once. We're just going to find the single next best split. Split the data and repeat it. Now, when we found the single best split, we were being greedy. Our algorithm is a greedy algorithm because it doesn't do the whole maximization at once. It just takes one small step in the best direction. Does that sound familiar? Yes, it should. Gradient descent takes one small step in the best direction. How do we know that gradient descent finds the best solution and not some local optimum? We don't. There's every chance the gradient descent will end up in some kind of local minimum. What's the solution to stop gradient descent ending in local minimums? Well, start it in lots of different places, use something called momentum or other fancy techniques. There are ways to do it. But greedy algorithms, which take small steps, where each step is the best single step without looking forward to see all the combinations of future steps, risk ending up with a model which is simply not the best model. Does that happen in linear regression? Well, actually, in linear regression with gradient descent, it doesn't happen, because the function that we're trying to minimize is convex. And it just so happens that if you're trying to minimize a nice convex function, then greedy algorithms will almost certainly get to the bottom fine. If it wasn't convex, you would certainly have a problem. We'll roll down the hill, we'll end up over there. How about decision trees? Well, decision trees are not a convex problem, so we're going to build our tree in a greedy way, and it might be we don't end up with the best of all decision trees. Does that matter? Well, not really, provided it performs well over future data. Can we do better? Can we try to make sure that we don't end up in local minima? Yes, we can. We can take smaller steps and more carefully, and that's what gradient boosting machines do. We'll see that shortly. By the way, even if we are doing this the greedy way and just thinking about one split at the time, it's not trivial. It's not trivial. To split the data, we need to decide which feature to split on and which level of the chosen feature to split. Imagine you've got 5,000 features, or some large number of features. Your algorithm, which is building your decision tree, every time it makes a split, has got to consider every single one of those features. And if the feature was just a binary category, that would be easy. But say the feature is some kind of continuous number, it's got to decide it's going to split age less than 45, age greater than 45, that's one split, but every single age might be a split. So it's got to consider hundreds, if not thousands of splits every time it makes a decision. So that's just to say, whilst we're being greedy, we've still got a lot of work to do in creating decision trees. And the people that created the first decision tree did amazing analytical work to be able to figure out how to do these splits with a minimum amount of computational effort. Just some thoughts now. What percentage of the data does each split use? If we start at the top, we have 100% of. We start at the top, we have 100% of the data. When we made the split, I think for the aviation data, it was 54% of the data went down one way, 46% of the data went down the other way. So when we were doing the split over here, we were doing the split based on 46% of the data. And of course, as we do more and more splits, we end up with less and less data. So at the end, we're going to be splitting leaves, which have a very small amount of data in them, based on what we see in the training data. Is that likely to be a really good idea? Are those splits likely to generate good predictions on test data that the model has never seen before? Almost certainly not, because when you have such a small number of examples in a leaf, you're bound to find a feature which looks like it's improving the accuracy of what you're doing in that leaf, but it's just likely to be random noise. So when do we stop splitting? Well, actually, there is nothing in the tree building algorithm to tell us when to stop. And if we carry on splitting all the way to the very end, we're going to end up with as many leaves as we have observations in our data. Each leaf is going to be totally overfitted to its own experience. That's going to be a really bad idea. What is the step size for a decision tree? If we compare a decision tree to gradient descent, when we make a split in our decision tree and we find probabilities or sale prices in the new split, how much do we listen to what we're seeing in each leaf? Well, the answer is we listen to it 100%. We see what's in the leaf, and that's what we use for our prediction. That's very different to gradient descent, where we choose a very small step size to try and make sure that we just go down a small part of the hill which is still sloping downwards. In the basic decision tree, we split forever. We have massive step sizes. If you had massive step size in gradient descent, you would probably just end up in a completely wrong place. It's not totally surprising, therefore, that if we're not careful building decision trees, we're going to split forever, always paying full attention to the smaller and smaller amounts of data in each leaf. And yes, can a decision tree overfit the data? It feels like it's almost designed to overfit the data. We have to work out how to stop it overfitting the data. Just to recap, a decision tree is a set of rules. It's hard to find the best. It's NP hard to find the best. It's impossible. Instead, we choose a loss function. We recursively partition. We recursively make one partition at the time, which is the best partition we can make at that point, and we don't care about what's going to happen in future. And that's called a greedy algorithm. And we take big steps based on smaller and smaller partitions of the data, which is a really crazy thing to do. There is a parameter which controls the complexity of the tree, which has been implemented in R, but not in sklearn. It's called CP, which stands for complexity parameter. If we set CP very small, it gives us the most complex tree. If we set CP very high, it gives us a tree with no splits whatsoever, which is just an intercept model. What does this remind you of? Please tell me. It reminds you of lambda in penalized regression. All of a sudden, everything feels very similar. In penalized regression, we used gradient descent to take steps in the right direction of the model. We're doing something very similar here with decision trees. In regression, you can totally overfit, and we therefore needed a complexity parameter, something which penalized overly complex models, and something which we could vary to see the different models produced at different levels of penalization, and which we could then choose the best model based on some kind of train validation. We're going to see exactly the same is true here in decision trees, and exactly the same is true in pretty much every supervised learning model you try to build.